Hi, my name is Giulianna, and today I'm going to be talking about meromorphic functions in complex analysis. So a brief introduction. The way that the structure is going to work is I'll define what a meromorphic function is, and then we'll look at some examples and non-examples of these functions. And then I'll introduce the concept of a singularity at infinity, after which I'll state and give a proof sketch of a relevant theorem. And then I'll end by discussing an application of meromorphic function theory to the Riemann zeta function. So first off, the definition. A function f of z on an open set omega in the complex plane is called meromorphic if the following three conditions are satisfied. So first, there exists some set of points, z1, z2, etc., in omega with no limit points in the complex plane C. In other words, the points at which these poles are don't accumulate in C. The second condition is that f has poles at all of these points. And finally, the third condition is that f is holomorphic on omega, excluding these points from the domain. So what that means physically is that if we take the set omega and remove all of the points where the poles are at, from the domain, then f will be holomorphic on the new domain. So for the first example, the set of holomorphic functions f from omega to c are meromorphic. So the way we can see this is that we can choose all of the poles, the z1, z2, the points at which the poles are, to be the empty set. So there are no limit points, and then the definition is vacuously satisfied. So let's look at a more interesting example. Example 2. So the functions with finitely many poles are meromorphic on omega. So here, since there are finitely many poles, we know that they cannot accumulate. And this satisfies the definition of meromorphic functions as well. So what we're essentially doing in this example is removing the poles from the domain. So on to the next example. So consider the function f is 1 over cosine of z. F is meromorphic on C, and there are infinitely many poles, which I think is interesting. The important point here is that the poles don't accumulate. In other words, they form a discrete set of points. So in particular, the poles exist when cosine of z is 0. And this happens when z is pi over 2 times 2k plus 1, where k is an integer. So basically, these points are spread out. They are sparse, and they don't accumulate. And that's why this function is indeed meromorphic. So on to a non-example. If we consider the same function from above, but with the input of 1 over z, so 1 over cosine 1 over z, then f is not meromorphic. And the way to see this is that f has an accumulation point, namely z equals 0. So it's not an isolated singularity anymore. And the poles occur when z is 1 over this pi over 2 times 2k plus 1. So as k goes to infinity, the poles will be occurring at 1 over infinity, which goes to 0. And that's the intuition for why this function in particular is not meromorphic. So now I want to talk about singularities at infinity a little bit. So suppose we have a function f, which is meromorphic, and f of z is holomorphic for a large enough z. So what this means is that there exists some positive radius, capital R, such that f of z is holomorphic when z is outside of that radius. So for a large enough disk, the function will be holomorphic outside. And this equivalently says that the norm of 1 over z is strictly less than that radius. So what we want to do is define a function capital F. So capital F of z is equal to f small f of 1 over z on an open disk. And we define this disk such that the radius is 1 over capital R, and we remove the origin from the domain. So since the domain no longer includes the origin, capital F is holomorphic and has an isolated singularity at 0. So the definition of an isolated singularity at infinity is if capital F of z has an isolated singularity at 0, then we say that small f of z has an isolated singularity at infinity. And an interesting point is that if the singularity at 0 is removable or a pole or an essential singularity of capital F, then the singularity at infinity of small f is of the same type. So if one has a pole, the other has a pole. If one has an essential singularity, the other one has an essential singularity, and so on. So I want to move on to the theorem statement now. But first, I want to make a brief remark that not all meromorphic functions have isolated singularities at infinity. So considering the example we looked at before, 1 over cosine z, f is meromorphic, but capital F, being 1 over cosine 1 over z, has poles which accumulate to 0. All right. So the theorem I want to discuss states that a function f of z, if it's meromorphic on C with a removable singularity or a pole at infinity, then f is a rational function. So a rational function is defined to be the ratio of two polynomials. And recall that polynomials are indeed entire functions. So I want to make a note here. The theorem considers the cases where the singularity is either removable or a pole, but doesn't discuss the case of an essential singularity. And that is because the theorem actually doesn't hold in that case. So if f has an essential singularity at infinity, then f will not be a rational function. And an example of this would be just f of z equals e to the z. Okay, so for the proof of this theorem, I want to introduce a lemma that's going to be used. And the lemma states that if f is an entire function with a removable singularity at infinity, then f of z is constant. And the way that this proof would go is that we know f is bounded outside of a disk of radius capital R, since there's a removable singularity at infinity. We also know that f is bounded inside the closed disk by compactness, and therefore f of z is bounded on all of C by the maximum of the two bounds. Since f is bounded in entire, we can apply Liouville's theorem to see that the function is constant. So the proof of the theorem is quite technical and long and involved. So I'm just going to talk about the main ideas that are used, and then I recommend looking at the write-up to see all of the details and technical elements of the proof. So let's get started. The first main point is that f of z has an isolated singularity at infinity, and this implies that f of z has finitely many poles. And we can prove this by contradiction and using compactness. And the second important point is that at each pole, zi, we write f of z as a index negative ki over z minus z naught to the power of ki, and the sum all the way to a index negative 1 over z minus ci plus gi of z. And we then define fi of z to be f of z minus this gi. So next, at infinity, we locally expand at 0. So capital F of z is equal to a index negative k infinity over z to the k infinity, the sum all the way until a index negative 1 over z plus g infinity of z. And we then define f infinity of 1 over z to be, small f infinity of 1 over z to be capital F of z minus g infinity of z. And then the last step in the proof is that we define capital H of z to be f minus f infinity minus the summation from j equals 1 to n of f of j, fj of z. And we see that h of z has removable singularities at z1 all the way to zn and at infinity. And therefore, h of z is constant by the lemma. So we finally want to solve for f in the equation for capital H. And from this, we will conclude that f of z is a rational function. And we can see this last part by noticing that each term is either a constant or a rational function. So by linearity, f of z is also a rational function. And this concludes the proof. So meromorphic functions in complex analysis as a whole, so they can be thought of as a generalization of complex functions with finitely many poles. So previously in class, we focused on holomorphic functions and special properties and theorems that apply to these functions. Meromorphic functions are a looser set in which the points, so yeah, they're a looser set of functions since there are poles, which are points where the function is not holomorphic. Yet we're restricted in the sense that the poles can't accumulate to a point that's inside of the domain of the function. So if we consider the case when the domain of f is C, a function is entire if it's holomorphic on all of C, and it's meromorphic if it is entire except for at isolated singularities, which are poles. The last thing I want to talk about is applications. In particular, I want to introduce the Riemann zeta function. So we can define capital R of z to be the summation over n from 1 to infinity of 1 over n to the power of z. And it's important to note that this function is normally defined where the real part of z is greater than 1, and it's holomorphic on this domain. So the theorem states that R of z can be continued across the boundary where the real part of z is equal to 1 of the half plane real part of z greater than 1. And it's a meromorphic function on the complex plane C, having the single pole at z equals 1 with a principal part of 1 over z minus 1. So what this means is that there's a simple pole at z equals 1 with a residue of 1. In other words, R of z over 1 over z minus 1 is an entire function. And lastly, I just want to say that there are many interesting applications of the Riemann zeta function in physics, statistics, and other fields. Thank you.